Hello everyone. Today's tutorial is about impact analysis. So as the name suggests, impact problem consists of a dynamic problem. There will be time dependence of the problem and problem having the effect of inertia, and of course it is also impact between two bodies, so it is also a contact problem. So this tutorial is divided into two parts. First of all, I'll talk about modeling contact in Abaqus. I'll be using finite element tool Abaqus, and there I'll be solving some simple problem, and after that I'll go to I'll try modeling a impact problem. So contact problem, for contact problem I will consider a very simple problem, a Hertzian contact of a linear elastic solid and with a rigid sphere. And for this problem, analytical solution for the applied force and the penetration or the settlement of this point is known, and we'll use Abaqus to model this problem and compare the result with the analytical solution. For modeling purpose, we will consider we'll take advantage of the symmetry of the problem, since it is axisymmetric. This can be idealized as the axisymmetric problem, and to reduce the computational cost. And after we do the numerical modeling, we will get this result for the applied force and the displacement, and then we will compare with this analytical solution as provided by this expression. Okay, now let's go to Abaqus and create a model. So the model will be consisting of two parts, one for the deformable solid, another is for the rigid rigid body for the sphere. So first, for the deformable body, I will provided the dimension shown the dimensions to be considered in the just few minutes back. So let's create the geometry accordingly. So we'll consider axisymmetric. First we will consider a deformable body, and it is a 2D, so it will be called as shell. Okay, the first part, of course, to create some construction lines. And all right, so rectangle will start from 0, 0 and length 0.5, height 0.6, and done. All right, and okay, we'll need to create some material properties. Mechanical, we are going to consider to be elastic, and the material properties provided considered to be 115 gigapascal, so 115 E3 megapascal, and percentage of 0.31. Okay, okay, better to create okay. Before doing something else, let's also create some partition which should be useful for mesh refinement and other stuff. All right, and for refining the thing, enter thing, and maybe let's create a surface for contact. We need to create, that's it. Now we'll create a section for solid, because this is a 3D axisymmetric problem, so by definition it should be solid. Okay, and assign the section to the entire thing, and done. Now what we will do, we'll go to mesh module, set part, say 0.05 for enter, and set edges for this local region, so 1/10. Mesh control, alright. We like to get say quad mesh, okay, alright. Okay, we may reduce the size a little bit. Okay, and alright, now let's create another part for the rigid part, rigid sphere, and we'll try to keep a consistent dimension. So we know the top of the plate ends at 0.6, so okay, it is asking for the center point, and we know the diameter of the sphere is 0.4 mm, so it should be 0.6 plus 0.2, 0.8, and 0.6 plus 0.4, 1, and it is here. We'll trim it, we only need half of the segment, okay, and we bring these two parts together. Yes, it's perfectly located, see. Now okay, now this is a rigid part, right? For the rigid part we need a reference point, and let's consider this point to be reference point. Means because the entire body is rigid, so we are defining a point which will control or which will decide the displacement, the rigid body displacement of the entire body. Okay, now after that okay, we also need to mesh this geometry, and yes, and we also need to do something else. We to define contact we need some surface, and we want the outer surface, so yellow. And now go to the interaction module and create a contact between the sphere, where this is the master surface, and we can choose anything, and this is the top part of this of the deformable body as the slab surface. Continue, and let's consider small sliding and create a contact property. Use the default ones. Okay, we want the tangential behavior like the frictionless contact, and for the normal use the default hard contact. Okay, all right, so contact has been defined between this sphere which is modeled as asymmetric rigid, and the deformable solid which is modeled as axisymmetric deformable body. And we have defined the contact, we have mesh. Okay, we need to create okay, we also need to create some sets, and we say we like to apply some displacement here and record the forces there, right? We create to apply the displacement in a small increment, and okay, let's create some more sets for to apply boundary condition at the bottom of the deformable body. Alright, we now create the boundary condition for the bottom. We like to fix the bottom of the solid, right? Okay, use all the to be constant, and we like to apply some displacement at this point. We can do the same thing by applying some force as well, so that's not a problem. Okay, we want all other displacement other than the vertical to be 0. So for vertical we choose a value of small value of say 0.01. Okay, so as you can see, it will not move in horizontally, it will not rotate about the z axis, like in plane rotation is 0, but it will only apply a vertical displacement, vertical downward displacement. Okay, after we do this, now our model is ready. Let's create a job. All right, let's see. We forgot to do one thing. We like to get the load deformation response. So for that we need to define some history output, and for this we like to get the vertical displacement and vertical force at the reference point. Okay, and let's rerun it. These are the data file where you can see if there are some mistake in the input data, it can be found here. And message file, it shows up, talks about the different convergence, and status file. Okay, let's go to the result. Right, okay, looks like we have some result. Okay, looks good. You can see the pressure contours due to contact. Now okay, this is something from the old file. Now let's get the history output, and for history output we have this reaction force and this displacement. Save as, combine, plot. Okay, as you can see it is okay, it is a bit weird, like displacement value, because displacement is vertical downward, right? So 0 to minus 0.01 and force increases from 0 to minus 80. Now how we can do export this result? We can go to a report xy and okay. So now we got this data written to abaqus.rpt file. It is external file to write the data. Now we can use that data and take to any programming. We can use any programming language like Python or MATLAB to plot the result and compare with the analytical solution. All right. Now what we'll do, we'll post process the result to compare with the analytical solution. So for that I am using a Python script, and this is the Abaqus output, and this is the actually analytical solution, right? And let's see where are we. Okay, it looks like a very good comparison. It is analytical and numerical, and so okay, I've just summarized the results here. So compare with the analytical solution, and these are the pressure contours as you have seen few minutes back. Okay, so the contact formulation, contact modeling in Abaqus for of course a static problem seems to be working well, and we could compare the results with the analytical solution. Next, will talk about modeling an impact problem. Now we will talk about dynamic impact problem. It is a impact between two deformable solid. It is a disk made of linearly elastic solid. We are considering material properties of this disk to be that of the steel, and it will be impacting on a aluminium of which is assumed to be a elastic perfectly plastic solid. All the material properties and all the dimensions are taken from this paper by Vecroville and Nue. We are considering the diameter of this disk to be 10 mm, and it is impacting on this aluminium base at a initial velocity of like 1200 millimeter per second, 1200 meter per second, sorry. So it is about 1.2 million millimeter per second, and we are planning to simulate the problem for 40 microsecond, and planning to use a time increment for 0.1 microsecond. Okay, we assume that thickness of this disk and this plate or the base is very high, like it's a very thick specimen, and we will be assuming plane strain state to model this problem. And okay, now we will go to Abaqus, try to model this problem following these material properties and geometric dimension as listed down here. Okay, let's start doing the modeling. So we will create a part of 2D planar deformable solid. First thing first, we will create some construction lines. Sorry, 0, 0, 1, 0. All right, we will follow the dimension as it is provided. We will start from -30, 0 and go up to plus 30, 40. All right, and the disk is located about 5 mm above this. The gap between the disk and this plate or the base is about 5 mm, and the diameter of the disk is assumed to be 10 mm. Okay, let's do it like this. Center will be here. Okay, let's see the dimensions. Okay, 5 mm, good. And we need the vertical distance between these two. Okay, looks good. All right, then we have created the geometry. Now what we need to do, create a few sets to assign material properties and boundary conditions. Okay, first for the disk, this is disk. Second for the base, this is base. Next for a reference point in the disk which will to be monitored during the simulation. What else? We also need to create few surfaces for contact. I think this is good enough. Now let's create few material properties. First for steel, we are following the data provided in the paper mostly. Density of the steel provided as 7850 E minus 12, elasticity 200 E3, Poisson's ratio we assume to be 0.3. Okay, we'll make a copy of this and make it aluminium, and aluminium is elastic then perfectly plastic. Okay, of course the density and other parameters are different. Density is 2700, elasticity 78.2 E3, and of course there is plasticity as well. Okay, yield strength is 300 megapascal. First entry will be 0, and what is the yield strength at 0 plastic strength. Then we will use some small increase to give a very small hardening, and we use a very large plastic strength. All right. Okay, now we need to assign, create a few sections. Say this is section for steel. We'll use to be solid and steel, and we'll create another section for aluminium, material to be aluminium, and now assign the section to the corresponding sets, and for the base it is aluminium. Okay, we should also create a few other sets to define boundary conditions. Right, bottom. Okay, now we go to assembly, done, go to step module, create another step. Now we like to do dynamic simulation. We will use dynamic implicit. One can try with dynamic explicit as well. Okay, we'll use dynamic implicit because implicit algorithms are stable, and we plan to use a maximum time of 40 microsecond and an initial increment of say 0.1 microsecond. And okay, step definition complete. Now we need to define interaction, right? So between this disk and this plate or this base, and surface to surface contact. Master surface is the one which is impacting on it, and we'll use node region because it is supposed to be, there's supposed to be a lots of deformation, and different region of this base should be in contact with at least theoretically contact with outer surface of the disk. We will use the node region, the entire node region of the base. Okay, of course we need a property, inter-contact property, and for similar to previous example, with tangential behavior like frictionless and normal behavior will use a hard contact, and let's keep a penalty. I mean, there are many ways of enforcing, because contact is basically a constant. We are implementing a constant relationship with contact constant, and there are also many ways of implementing contact constant, like one of them is a penalty method. Of course there are other options like Lagrange multiplier and other options. So penalty method, let's try with penalty method. You can try other options to see what is the effect in the solution, in the convergence and other things. Anyway, all right, now we'll go to the load module and create a few boundary conditions for stability and other thing. Let's do it. We like to fix the bottom, done, and we like to, okay, no other boundary conditions, but we have an initial condition, initial velocity for this disk, and for this we will select the disk. Initial horizontal velocity is 0, but vertical velocity is 1.2 ES6, and it is vertically downward. Of course it is a very this disk at very high velocity initially. Okay, now let's go to mesh and we'll see it part. Okay, maybe it will be too far. Okay, looks good. And we want the element to be all quad, like 4 noded elements. You can check the mesh, what is the total number of elements, nodes. So it has used, okay, we need to change this element, it is considering plane stress. To do that, go to element type and select all and make it plane strain, because that is our assumption that we like to consider plane strain for thick specimen, and we are considering linear element. All right, now okay, I think we are ready to create. Okay, let's do one thing, let's delete all the previous jobs to make it clean and create M2 and submit. Right, it is running. While running the simulation, we can also have a look at the results. You can see there are lots of mesh distortion primarily because of the plasticity. And okay, as you can see, there are lots of plastic strain in aluminium, right? And the plastic strain values are quite high, in the order of 5, 6. There is a huge plastic strain. And you can look at the von Mises stress, and of course steel is elastic and the stress values will be very high there. We can remove the steel disc. Okay, and you can see the evolution of the stresses with time. Oh, too much deformation, right? Okay, this is the evolution. All right. Okay, we forgot to do one thing. In the shape module, we like to also monitor what is the displacement of this point, right? So for that we need to define a history output request, and we like to get vertical displacement of this point. And by default, Abaqus compute the energies, okay, for the entire model, total energy, different energies. We will see like what the result look like. But anyway, we need to rerun the simulation. It will take a minute. Okay, it is almost done. 33 microsecond. It will take a few, maybe 1 minute more. Okay, Abaqus is using automatic time increment. So okay, it is done. Let's go there to see the result. Okay, we have seen the other results, like we have seen this result earlier. This is the von Mises stress we like to see in the aluminium only. So initially at contact it is around 5 microsecond. At 8 microsecond you can see lots of stresses and penetration of aluminium by the steel disc, and of course it it comes with lots of plastic strain, right. Now let's have a look at the history outputs. Okay, so in history output we have, we are primarily interested in what is the different displacement of the lowest point of the disk. Okay, so as you can see that maximum displacement minus 30 mm, but there was initial gap of 5 mm between the lowest point of the disk and the base, the aluminium base. So maximum penetration is in the order of like 25 mm. Okay, you can compare these numbers with the data provided in the paper as well, although there are minor differences in the input parameter. And other things we like to also see, like different energies. Okay, how to see those? Okay, again go to dB history output. So there are lots of different energies already listed, like this is a kinetic energy, all K means total kinetic energy of the system. Also we like to see the plastic dissipation, like what is the plastic work due to the plasticity, like the plastic deformation of the solid. Here it is only for the aluminium. And we like to also see the strain energy. Okay, as is, and let's plot it. See, initially the entire thing is about kinetic energy, because the steel disc has initial velocity. Because of this velocity there will be lots of kinetic energy, and you can check this number by doing like half mv square, like v is the initial velocity, m is the mass of the disc, you can calculate that, and from there we can, okay, and the kinetic energy is converted to okay, this is the plastic dissipation and this is the strain energy, elastic strain energy, right. Because elastic strain energy is very small, because there is elastic deformation is significantly small. The most deformation is plastic nature, because there are lots of plastic strain, as you can we have seen already. Now if we like to compute what is the total energy in the system, so we can do from here, like if we like to do some post calculation on the xy data, like the generated data, we can use Abaqus functionals, like you can use the Abaqus as a calculator. Okay, alright, add to expression, save as, and I will write it as sum of E. And now let's plot everything together. Alright, as you can see there is a small decrease in the total energy of the system. Okay, why this is happening? Okay, this is now beyond the scope of this tutorial, we can discuss it later somewhere. Anyway, now so far we have simulated a dynamic impact problem of dynamic impact between two deformable solid. One is elastic, another is plastic elastic steel disc, and plus elastoplastic aluminium, and we using contact, we are using contact formulation in Abaqus to ensure that forces and other things transferred from disc to this aluminium base. and we are not modeling damage or anything. All that huge deformation you are seeing because of the plasticity, evolution of the plasticity in this aluminum base. And we also show how to compute the energies and how to get the record the displacement of a specific point in the disk, and with this you can also compare this result with the data provided in the paper. All right, that's all. Thank you so much.